Hello and welcome to today's ACM Learning webinar. This webcast is part of the ACM's commitment to lifelong learning and serving the over 100,000 computing professionals and students who are ACM's members. I am Indira Guzman, Professor of Information Technology Management and Director of the PhD program in the Glenn Jones College of Business at Trident University in California. I'm also currently Information Director for SIGMIS, the ACM Special Interest Group on Management Information Systems. My research interests include the impact of IT in organizations, IT occupational culture, IT workforce, IT security workforce, information security auditing, business intelligence, and performance assessment in higher online education. You can learn more about me in the bio window on the left side of your screen. For those who may be unfamiliar with ACM or what it has to offer, ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Centers resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides timely computing information published by ACM, including Communications of the ACM and Q magazines. Access to the ACM Digital Library, the world's most comprehensive database of computing literature, and international conferences that draw leading experts on a broad spectrum of computing topics. Support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Infosys Foundation Awards. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items shown in the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel on your screen, you will find a number of additional widgets and resources. If you are experiencing problems with the slides or audio, please press the F5 key in Windows or Command R if you are on a Mac, or refresh your browser on a mobile device. Or you can close and relaunch the presentation. To control volume, adjust the master volume on your computer. And if you have questions during the webinar, please type them into the Q&A box at any time during the webinar and click the Submit button. I will organize the questions as Tom speaks, and he will reserve time at the end of the presentation to address them. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. And check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you will see a survey open in your browser. Please take a minute to fill it out and help us improve our webinars. You can also use the Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag ACMLearning. We'll be watching for your tweets. Well, today's presentation is Fail Better, Radical Ideas from the Practice of Cloud Computing by Tom Limoncelli. Tom Limoncelli is an internationally recognized author, a speaker, and system administrator. His most recent book is The Practice of Cloud System Administration. His past books include Time Management for System Administrators and The Practice of System and Network Administration. In 2005, he shared the Usenix Lisa Outstanding Achievement Award with Christine J. Hagen. While at Google, he was a site reliability engineer for projects such as the web crawler, Block Search, Office IT deployments, and the Ganity project. Tom works in New York City at Stack Exchange, home of serverfall.com and stackoverflow.com. He is also a member of the ACMQ editorial board. His column, Everything Sysadmin, appears in that magazine. Tom, without further ado, take it away.
Thank you, Dr. Guzman. It's great to be here today, and thanks also to the audience for coming to the internet to see today's presentation. I'm going to be talking about, as Indira said, radical ideas from the practice of cloud computing. Before I go into the presentation, let me talk about my second favorite subject, me. I've been a system administrator since the late 80s. I worked at Google for 7 years. I was at Bell Labs for 7 years. And between them, I was at a number of other companies and startups. And now I'm a site reliability engineer at Stack Exchange, which most of you are probably familiar with as Stack Overflow. And yes, I've written a number of books. Now, when you invite an author to speak in a forum like this, often what the presentation that they give is a thinly veiled advertisement for their book, and I assure you that that is not this presentation. If it was, I'd have a slide that was just a picture of the book, and I'd talk about it for a little while, and maybe I'd have the table of contents, and I'd explain that it's really 2 books in one. The first half is about building large systems, and the second half is about running large systems. But as I said, it's not that kind of talk, so I won't be doing anything like that. Now, this is a talk about the cloud, and so let's talk about the cloud. The cloud, the cloud, the cloud, the cloud. Yes, you know, we heart the cloud, right? Everyone hearts the cloud. I heart the cloud. My coworkers heart the cloud. Everyone hearts the cloud. And why do we heart the cloud? Well, I think it's very simple. It's simple because the cloud solves all problems, right? Oh, sorry, I'm being told that the slides aren't appearing. Is this better? Okay, good. Sorry about that. The cloud solves all problems. Talk to any marketing person, they'll tell you that the cloud solves all problems. But, you know, okay, enough silliness. You know, engineers often, we often don't like the term the cloud. And that's because it's an overhyped term, but also the term cloud it means different things to different people. So to executives, cloud computing often means that it's an elastic computing platform. It's the ability to expand, to add additional compute capacity dynamically. To consumers, cloud computing often means storing your information on other people's machines. Like someone might say, I have all my music in the cloud, and therefore I'm able to view it from any place, from my phone, from my desktop, wherever. But to a computer scientist, the cloud usually means distributed computing. And distributed computing is a relatively new way of organizing work and doing computation. To explain cloud computing, I'm just going to back up, do a little bit of history, because I think that's the best way to understand distributed computing by comparison to older ways of doing computing. So in the old days, computers were, big and large, and the point of this slide is that computers were something you had to go to. There was this one big computer on campus or in your organization, and you had to go to it to get any information or do your computing, so to speak. And even when computers got smaller, it was still, before they were networked, it was a matter of going to the computer to get work done. Then networks came, and networks begat the concept of client-server computing. So client-server computing is where you have your desktop, and it's running different software than is on the server. Your client is running software that takes care of client-related things like the user interface and stuff, and the server is taking care of server-related things like storage. So, for example, the first email system I ever used was on a mainframe, and it was everything related to email was on that one machine. You logged into that machine, and that machine had the software that both read email and stored it and transmitted around. Client-server computing, you have a separate email client versus your server. And even though this is kind of like, well, of course, Tom, that's how everything's done nowadays. Well, 20 years ago, it wasn't always done that way. So client-server computing was so successful that it really took off, and we needed bigger servers because if a client-server situation would say 100 users was a success, with 1,000 it was even better, and even with 1 million, even better. Why? Because of economies of scale and things like that. The problem is that companies, vendors weren't making servers that were big enough. And in fact, we hit the limits of certain physics of how we can make computing, how large we can make a server. So, so in the late 90s, distributed computing was invented, and this was a concept of we would take the work that needs to be done and divide it over many machines. Now, to do that, we had to have some way of coordinating it, and that coordination could be centralized or decentralized, but however it was organized, it let us divide the work over many machines. So for example, genomics, you might have hundreds of machines working on a data set. Each machine gets a little fraction of the data set. They do their work and forward their results to maybe a central machine or something. In web service, you might have, say, 10 machines, each taking 1/10 of the web traffic that's coming to stackexchange.com. And even though they're all driven off of a common database, each web server that we add to stackexchange.com is able to add to the capacity of the total system. Distributed computing isn't just about processing websites or doing computation. It can also be about storage. So, for example, at Gmail, there isn't one huge machine that stores all the Gmails, right? There are thousands of machines. Each one stores a fraction of the number of messages that are stored in across all of Gmail. So distributed computing can do more work than the largest single computer out there. It can get you more storage, more compute power, more memory, more total throughput. And the proof for this is kind of easy. If I have a distributed network of computers and you say, well, I can build a single machine. If you successfully build a single machine that's bigger than my distributed network, no problem. I'll buy 10 of those machines you just built, put it into a distributed network, and now I have an even larger machine. So distributed computing is able to scale and scale and scale. Now, what computer scientists learned is that with more computers, we had more problems. So we had, for example, going from tens or hundreds of users to thousands of users. And when you do that, you have bigger risks. So a small outage, in my first job, if there was a small outage, it affected maybe 100 people. They might not even notice if they were all at lunch. When you're a huge website like something like Facebook or Google or something, if you have an outage that affects everyone, that's millions or billions of people, and it becomes a headline in the newspapers, right? So the risks are bigger because you're affecting more people, and failures are more visible because, as I said, it could be a newspaper headline the next day. But also, automation becomes mandatory. If you are managing thousands of machines, you have to automate your processes. If you have 1 or 2 machines, sure, you might be able to do things manually, but that's not going to scale to the size of large distributed networks. In fact, companies like Facebook and Google could not possibly hire enough people to do everything that's done in system administration if they had to do it manually. Also, cost containment becomes critical. If you can save $10 per machine and you have thousands of machines, you're talking about a lot of money. And in fact, and this actually happens. You know, there's in small environments with 1 or 2 servers, they might get a slightly fancier video graphics card, which is kind of a waste because you're not going to play video games on a big server. But okay, so maybe you wasted 50, 100 bucks. Who cares? But when you're talking about thousands of machines, you know, an extra $100 on thousands of machines can be millions of dollars. So in response, computer scientists came up with a number of really radical ideas of how to solve these issues. And in fact, so let's talk about them. So dealing with risk in distributed computing, we don't just talk about reducing risk, we talk about improving safety. Can a distributed system be operated safely? And now you're not talking about risk. You're actually, a lot of the comparisons that work well are to an airline. Can you operate a large, you know, 747 safely? Well, yes, you can with certain techniques, and it's the same paradigm when you're paradigm shift when you're dealing with a large distributed network. Reliability becomes a competitive differentiator for your company. In the 90s, businesses discovered through great research that people don't go to a website that's down. Think about that for a second. And in fact, not only do they not go to a website that's down, but when it's down, they then go to the competitor's website, and often they don't come back. So reliability became a really key, important thing for businesses. Also, distributed computing begat a lot of new automation paradigms. You hear a lot about infrastructure as code and configuration management. This all came out of distributed computing. And lastly, the cost and economics. Companies dealing with thousands of computers were able to look at their economics very differently. So if you notice, companies like Facebook and Google, they build their own hardware because if they can, by being the company that designs their own hardware, they can shave off a dollar here, a dollar there, and it really adds up. They can write, they can do certain things differently because they're thinking at a big scale that is going to save money. But the most interesting thing that distributed computing researchers found in the 90s is that when you're dealing with really large systems, you have to make peace with failure. You have to make peace with failure because everything's imperfect. Everything is going to fail eventually. From the littlest parts and components, they're going to fail. Networks are going to fail. Bigger system, you're going to have system-wide failures. Code is imperfect. You have to assume in a large system that there are going to be bugs. And in fact, unlike, say, some piece of desktop software where if there's a bug, okay, maybe we'll fix it in the next release. In a large distributed system like a Google or Facebook or Yahoo, you need different ways of fixing bugs. You need, for example, you need to be able to quickly be able to put in a workaround if the actual bug can't be fixed for days or weeks. And also, people are imperfect. The larger and more complex the system you have, the more likely it is that people will be part of the problem. So, so because all of these things are imperfect, we must make peace with them. In fact, another way of thinking about it is we have to learn to fail better. If failure is going to happen, then we have to get really good at it. So when I was doing some research to prepare for this talk, I thought, maybe I should go back and research what are some of the older systems that were known for being very high reliability, and what do those have in common, or what can we learn from them? And I stumbled upon a lot of articles about the Lucent 5 ESS phone switch. This is the big computer essentially that ran the international telecommunication system. Something like 80% of the world's global phone system was controlled by 5 ESS. And it had incredible uptime. In fact, a number of these machines were known for going multiple years with zero downtime. And I thought, wow, that's fantastic. And they were doing this in the 80s and the 90s. Well, the more I read about it, the more I learned, and I soon discovered that here was their secret to for building such a reliable computer. First of all, they had incredible quality control. But secondly, they defined an outage as, they didn't count outages that were planned. If you had to take the system down for a planned maintenance cycle, that didn't count towards your downtime statistics. So in other words, you can buy the best, most reliable computer in the world, and it's still going to fail. And even if it doesn't, you're going to have to take it down for maintenance. So since we need to learn to fail better, I'm going to spend the rest of this talk, in fact, I'm going to spend the rest of this talk on 3 different ways to fail better. And so those 3 different ways are, first, use cheaper, less reliable hardware. Second, if a process or procedure is risky, you should do it a lot. And third, don't punish people for outages. Now, some of you watching this webcast might be thinking, oh, these are 3 mistakes that businesses make, and Tom is going to talk about how not to make these mistakes. Actually, these are things I'm going to encourage you to do. So, let's dig in. Let's talk about the first one. Use cheaper, less reliable hardware. Now, the easiest way for me to explain this is by analogy. I travel a lot, and when I travel, I often rent a rental car. And if you've ever rented a rental car, the people that sell it to you or rent it to you, they try to get you to buy 4 different kinds of insurance. Now, it would be fiscally irresponsible of me to get all 4 kinds of insurance, especially since my personal auto insurance covers any rental car that I get. Not only that, but my homeowner's insurance also covers any rental car that I get. Oh, and if I rent this car using an American Express card, that also covers any rental car that I get. So if I were to purchase this insurance, I would be spending money at many different levels, and that would be redundant and fiscally irresponsible. So how does that relate to distributed computing? Well, let me tell you another story. Recently, a friend of mine came to me and he said, Tom, I want to build a big website for this company I'm starting, and I'd like to show you the plans we have for the website and get your feedback. I said, sure, I'm interested. So what are you going to do? And he said, well, we want this website to be super reliable. So we're going to buy a really high-end server, not going to spare any expense on the server. And I said, okay, so what else are you going to do? And he said, well, we're going to put all the storage on RAID. We're going to buy the finest RAID controller to connect all of our hard disks. And we're going to get the dual power supply option so that it can take power from 2 different sources. And if either of them fails, the system will keep running. And we're going to put the system on an uninterruptible power supply. We're also going to buy the gold maintenance package for all of this hardware. And yeah, because gold maintenance, you get 4-hour response time from the vendor. Not only are we going to do all of that, but we're going to buy 5 of these machines, and we're going to put them behind a load balancer. So any one of those machines can go down, and the load balancer will just send any web requests to the other 4. Now, there's a problem with that, which is our software currently isn't designed to work behind a load balancer. So we're also going to spend money on developer time, making changes to the code so that it works in a distributed environment. And let's see, is there anything else we can do? Yes, we're going to buy 2 load balancers so that there's no single point of failure. Now, if you think about what they're doing with this design, it's much like renting a car and buying all those different kinds of insurance when you're double covered. We are spending money on every level instead of spending money smartly. Now, what we learned in distributed computing is that it's better to do reliability through software. If you write software that can work around a problem, you can deploy that software to every machine in your network for free because you wrote it, as opposed to if you buy the top software, if you do your resiliency through hardware, you have to buy that hardware for every machine that you install. So you can buy the best hardware, and you still have to write code that makes your software work in a distributed environment. Why not just write the code that lets your software work in a distributed environment? And when you do that, you design your web servers differently. You focus not on buying the most impressive, most reliable hardware, but on the most efficient hardware. And efficiency takes into effect not just being able to process a lot of requests per second, but also you can look at the entire picture. How does this, which server uses the least amount of electricity, uses the least amount of floor space? Data center space is very expensive. Cooling is expensive. All these things add up, and you actually end up being able to focus on total cost of ownership, which is a much better thing to do business-wise than just always striving to buy the most reliable system. In fact, if you're always striving to buy the most reliable system, to be honest, there's always a salesperson that's going to sell you something more expensive because, hey, just spend this many more dollars and it'll be more. We'll add these features that'll get you that resiliency. Now, these techniques work for large grids of machines, but also for everyday systems too. And there's also doing these kind of resiliency techniques are usually cheaper when you do them in a large environment. So if I had, on the left, we have a load balancer that's serving 2 web servers. Now, each of those web servers, if one of them dies, the other one's going to take over responsibility for its work, which means we have to leave those machines half underutilized, or we can only utilize half of the machine because if one goes down, we need enough headroom or spare capacity to take the load from the machine that died. Now, if you're doing this on a much larger basis, if you have, say, on the right where we have 10 machines, the headroom you need to leave on each machine is only 10%, which is, so you're going to save a lot of money. I mean, would you rather go to your boss and say, hey, we're going to buy this system and leave half of it unused except in emergencies, or we're going to leave 10% of it unused except in emergencies, right? That second thing is going to be much more cost effective. And in fact, that's why companies like Dropbox, with their distributed computing environment, can offer data storage often for free for a lot of users, and for enterprise users, less expensive than most small businesses can provide for themselves. So in conclusion, the right amount of resiliency is good, and too much is a waste. If you don't want to be in a situation where you're spending your way out of resiliency. If instead you're programming your way out of resiliency, you're going to have a better economic model for what you're doing. And the example I've been giving over and over again here is some kind of load balancing technique. And that's just one distributed computing technique that exists. There are many other ways. And a related story to that is something that happened at Google. When Google was a young company, they had this application that they were able to do significantly faster than any of their competitors. And the reason they were able to have the application run so quickly is that instead of storing their whole database on disk, they stored all their information in RAM. And RAM is a lot faster than disk. So they needed to buy a lot of RAM. And in fact, they were buying terabytes of RAM because for every certain number of users that they had, they needed to build another cluster of computers. And so they were building these clusters one after the next and putting them all over the world. So their purchasing department was constantly negotiating with vendors to buy more and more RAM. And one day, the developers noticed that, well, you know, RAM's pretty reliable. RAM has like a 1 in 10 trillion error rate in a running system. But when you have terabytes of RAM, 1 in 10 trillion happens a lot. So, so they updated their software to work around RAM errors. And they actually, I won't go into details, I can in Q&A, but so their software was able to work around bad RAM. And as a result, they were able to stop purchasing the expensive high quality premium grade RAM and instead buy consumer grade RAM, which is a lot cheaper. And so now they're building clusters and they're spending a lot less money every time they have to build a cluster. So that was great. And then one of their purchasing people called, he had a brainstorm and he called one of their RAM suppliers and he said, hey, so, you know, we used to buy the premium RAM and now we buy the consumer grade RAM, which is cheaper. Do you have two different factories, one that makes the really good RAM and one makes the consumer grade RAM? The person said, no, that's not what we do at all. We have one factory. We just make RAM chips. And then when we're done, we test them. And if they pass 100% of our tests, we sell it for a lot of money as premium RAM. And if it only passes most of the tests, we sell it for less as consumer RAM. And he said, and the person from Google said, well, what do you do with the stuff that doesn't pass any of your tests? And they said, well, we throw that out. And the guy from Google thought for a second, and he talked to the developers, and he said, hey, could we use this, you know, kind of crummy RAM? And they said, yeah, well, you know, if it's good enough to just boot up minimally, we can handle the rest. So he went back to the RAM company and said, how much would you sell us the RAM chips that you normally throw away? And they laughed and said, well, pennies on the dollar. So now Google was buying, you know, for pennies on the dollar RAM that they had been paying much more previously. And their software worked around this issue. Now, when their competition realized that they were losing customers because Google was faster, they said, well, we have to be faster too. And they started buying RAM and re-engineering their system to run out of RAM instead of off disk. And since those competitors hadn't invested the time to make this software that could work around RAM failures, they had to buy the premium RAM. So this all became a competitive advantage. Their competitors were trying to compete in ways that required them to buy computers that were much more expensive than what Google was doing. So that concludes part one, use cheaper, less reliable hardware. And I hope I've convinced you all of that is one of the keys, one of the radical ideas that you can take home from distributed computing. So now let's move on to part two. If a procedure or process is risky, do it a lot. Now, I say this with confidence because there's a difference between behavior and procedure. Risky behavior is inherently risky. And that's different than a risky procedure. Risky procedures can be improved through practice. So, risky behaviors are inherently risky. Here are some examples of inherently risky behaviors. I cannot find a way for you to do these things ever any more safely. And that's because risky behavior is inherently risky. However, risky processes can be improved through practice. So here are 4 operational tasks that are very common but risky. And I assure you, as a system administrator, these kind of tasks can strike fear in our hearts and make us very nervous. But through practice, we get better at doing them, and they become less risky. So to explain this, let me tell you another story. As I mentioned before, I work for Stack Exchange, and when I joined the company, it was explained to me that the way that the Stack Exchange software works is, well, first of all, it almost entirely runs from a data center in New York, and we have a redundant data center in Oregon, which we can switch over to in case of emergency, if there's some kind of problem in New York. Another thing you should know about the Stack Exchange environment is that it's based on a number of products that all work together. Now, I come from a Unix, Linux background, but Stack Exchange is a mixture of Windows and Linux environments. So something that a lot of people don't realize about Stack Exchange, when you're reading our, the question and answer site or whatever, is that HTML is all generated from Windows systems. It's C# talking to Microsoft SQL Server, but that kind of technology often doesn't scale very well. So how do we make it scale? Well, we scale it by surrounding it with Linux for caching and security and change management and load balancing and a number of other things. Or as I like to say, we have a GUI Windows Center surrounded by a crunchy Linux shell. Now, when I joined, I was very curious. I said, okay, how do we do this failover from the New York data center to the Oregon data center? Now, I don't know a lot about Windows, but I do know that usually in a Microsoft product, if you need to do something, there's a button you click and it does it for you. So show me the button that you click to fail over from New York to Oregon. And they sat me down and said, well, Tom, it's not that simple. Yes, that's how we fail over the database, but that needs to be coordinated with also at the same time we have to switch over things in DNS and our caching servers and our CDN and many, many other things. And I said, well, okay, I'd like to learn this process. And they said, okay, well, we'll schedule a time where we'll do a failover. Even though the system is up and doesn't need to be failed over, we'll schedule one. We'll call it a fire drill. And they told me that it should take about 1 hour or less to do the failover, and that users would only see mere seconds of actual downtime. So we scheduled a Saturday. We planned on doing this, and did it take an hour? No, it took 10 hours. We learned a lot from doing this. First, we learned that it took 10 hours to do it. We learned that it required hands-on activity by 3 different teams from the company, my team and 2 other development teams. During those 10 hours, more than 30 bugs were filed. Bugs related to problems we found with the failover system, with databases and processes. A lot of those bugs that we found were just documentation bugs, that the procedure book for how to do this failover hadn't been updated in a while and had fallen out of date. The other thing that we learned, and this was so valuable, is we learned that the process could not be done if Nick was on vacation. Nick was our single point of failure. And that's a huge risk. What if Nick was on vacation or out sick or had left the company, right? So now some people would say, well, this is a very risky procedure. You should avoid doing it. You should try to do it as little as possible. But no, we were smart enough to say, if a procedure is risky, do it often. And we knew that by doing it more often, we would get better at it. So we did it more often. Now, as I mentioned, the first time it took 10 hours and we filed 30 bugs. The next time we did it, it took about 5 hours and we filed about 20 bugs during that process. The next time we did it, we got the process down to 2 hours and it took about, and we filed about 12 bugs during that process. And the most recent time we did the process, we got it down to 1 hour and only 5 bugs were filed. But that's good. Finding bugs is actually kind of good because that means we're noticing improvements that can be made. So why was it so good to take a perfectly working system and force it to fail over to our disaster recovery site? Well, each drill surfaced many areas of improvements. We filed tons of bugs, and each of those could be triaged and fixed. We also were able to give team members experience doing the process themselves. So Nick is no longer the only person that knows the entire process. Almost everyone on the team can do it. We also feel this is better because small batches are better. If you think about this process, because we hadn't done a failover in so long, there was a big batch of changes that had accrued in our system. And any one of those changes could have a bug in it. But when we start doing these tests, these failover drills on a monthly or every other month basis, the number of changes to the environment that can accrue is a smaller batch. And so the risk is actually reduced. And small batches are better for a number of different reasons. So it's not just that there are fewer changes in each batch, but if there are bugs, they're easier to identify. Anyone who's ever tried to debug software knows that the first step is you have to find where in the code is the bug. Well, if there are fewer changes since the last time we did the system, since we did the failover, then the places that we have to look to see where the bug could be is smaller. So we could actually do that first part of bug fixing faster because we have a smaller surface area to search through. Small batches also reduces lead time because it's easier to debug code that you've recently written. If you apply this thinking to software updates, like new software releases, if you do new software releases every 6 months, the code that you're trying to debug might be 6 months old. If you do software releases every 1 month, then the code that you wrote is still fresh in your mind when you go to debug it. As we saw in this recent example at Stack Overflow, the environment has changed less between fire drills. But what's really exciting to me about the small batches principle is recent psychological research that has found that employees that work in a small batch environment are happier and more motivated. A lot of that comes from the fact that there's more instant gratification for everyone involved. When you write code, if it's released to production in days instead of months, you get that positive instant gratification feeling that really helps motivate people. So I kept relating small batches to software upgrades. Let's drill down on that a little bit. In the traditional way of doing software upgrades, you often have maybe a software release every 6 months or every year, or back in the 90s, Microsoft Office came out. They had a new release every 3 years. Now it's much faster than that, which enables operations organizations or IT organizations to work in a much closer to a small batches environment. But in that traditional software upgrade, big batch environment, it's months of plannings. You have tons of incompatibility issues because so much has changed between software releases. You might not be sure what is incompatible. It can be very expensive. Your mistakes are very visible because it's a big change. Therefore, any mistakes that happen are very visible. And often by the time we're done, it's time to start all over again. Now, distributed computing could not possibly work in an environment where software releases were every 6 months or every 3 years. In distributed computing, there's a high frequency of updates. You are often releasing new versions of the software every week or every day, or in some cases every hour. Also, software upgrades just have to be automated. If you're upgrading the software on 10,000 machines, you can't possibly do that manually. It's also becomes easier to fix failures if you're doing a lot of small releases. If there's a bug in the system and you have to wait 6 months to do a new software release, that's difficult. You're living with that bug for 6 months. But if you're doing rapid releases, then if you find a bug one day, it could be fixed, and the fix could be in production the next day. And because software releases are so easy to do, because they're automated and done rapidly, et cetera, they become cheaper to do, which means it changes your business because you can now experiment with software. You can try doing, if you're not sure how a feature should be done, you could actually do it 2 different ways and try it 1 week one way, 1 week another. They do a lot of A/B testing in distributed computing. And none of that would be possible in a big batch environment. So big bang releases are inherently risky, and small iteration releases reduce that risk. Another way to think about this for the more mathematically inclined is that risk is inversely proportional to how recently a process has been used. If you haven't done something in months, it's a lot more risky than if you do it every day. If you do data backups of your system, a very common thing is to not be sure of the quality of those backups. But if you've done a successful restore of some data in the last week, you have a lot more confidence. If you haven't touched those data backups in a long, long time, then it's very risky. And in fact, at Stack, we actually have an automated process that after backups are done, we immediately do a restore to a test system and run a number of tests to make sure that the data that we restored is complete. You know who's really good at this? Netflix. Netflix has a system called Chaos Monkey, which every couple minutes picks a random machine and reboots it and tests that all their resiliency mechanisms kicked in and did the right thing. And they run Chaos Monkey during the day, 9 to 5, Monday through Friday. They don't run it on the weekends because their goal here is to discover those bugs in their resiliency system when everyone's awake and in the office and presumably sober, as opposed to if they just let the bugs reveal themselves, then they're more likely to reveal themselves, say, on the weekend when the new episode of House of Cards is out and everyone's rushing to their system to view it. So they actually have what they call the Simian Army. Chaos Monkey, as I mentioned, reboots hosts. There's also Chaos Kong, which simulates data centers being down, and Latency Monkey, which adds random performance delays to their network so that they can determine that their new code has an error situation that happens with slower networks or overloaded networks. They can learn those situations during the day when everyone's awake, as opposed to at night when the new season of House of Cards comes out. So that concludes part 2. If a procedure or a process is risky, do it a lot. So now let's talk about part 3. Don't punish people for outages. Now, as I mentioned earlier, we will always have outages. There's a whole host of reasons. Parts are imperfect. Everything's imperfect. But what's important here is that getting angry about outages is equivalent to expecting them to never happen, which is irrational. Yet our industry is full of outdated attitudes about outages. We have an expectation that things will be up 100% of the time. We fire people. There are companies that after an outage, they fire a person because management wants to prove they're serious. And as a result, people hide problems because the last person to touch the system is often blamed for any problems it has. People stop communicating. It discourages transparency, and small problems get ignored, which therefore turn into big problems. In fact, this manager who thought he was doing such a good job by proving how serious he was by firing someone as a result of an outage has actually created the environment, the exact environment that describes a culture that creates more problems, the lack of transparency, the lack of communication. So instead, distributed computing and DevOps has learned that we need new thinking on outages. We need to not expect 100% uptime. We need to anticipate outages by using strategic resiliency techniques in software, do fire drills like I mentioned before, and as a result, we encourage transparency, we encourage communication. Small problems get addressed while they're small, so they don't even grow into big problems, and therefore overall uptime is improved. Not only do we communicate about our problems, but we flaunt them. After an outage, we write up a postmortem document that explains what happened and what we're going to do in the future to prevent it from happening again. Therefore, we put the focus on taking responsibility for fixing long-term problems instead of blame. Often some organizations have a policy of blame and shame after an outage. And these next couple slides, which I'll just flip through, this is an actual postmortem that we generated at Stack Exchange for an outage that happened. The most important part of this report that we write up after every outage is the last part, where we list what went right, what went wrong, what we're going to do in the near future, and what do we need to do in the long term to prevent this. And as a result, when that postmortem went out, this is the email that I got back from a coworker. Anna wrote, "I don't know about anyone else, but I really like getting these postmortems. Not only is it nice to know what happened, but it's also great to see how you guys handled it in the moment and how you plan to prevent these events going forward. Really neato, thanks for the great work." I think it's really amazing that in an environment where you have this new thinking on outages, the response I got from coworkers was not, "Oh, we had this outage that's bad," but "Really neato, thanks for the great work." So I hope now I've convinced you that people shouldn't be punished for outages. And that concludes the three take-homes that I wanted to talk about. Cloud computing, kind of a marketing thing, but when you hear that term, think distributed computing and all the great things that comes from that. Use cheaper, less reliable hardware because we're going to create a resiliency through software when possible. If a process or procedure is risky, do it a lot because practice makes perfect. And don't punish people for outages. Instead, create an environment that focuses on accountability and resiliency. So that's the time we have. I'm gonna skip a bunch of slides and go to the Q&A. But I do want to say that these techniques are not so radical. In fact, these are all techniques that come from the 50s and 60s that the Toyota manufacturing model actually invented a lot of these, and that led to the lean manufacturing movement, which led to the lean startup movement and lean IT, which is basically what DevOps is. DevOps is the application of the lean principles to IT. So really, these aren't the radical ideas. These are the very reasonable ideas of cloud computing. Thank you very much.
Thank you, Tom.
And now, sorry.
Yeah, this was a great presentation. Thank you for all your insights and the great examples. I have a few questions from the audience. So the first question is about your book. Do you have any plans to write a second edition of Time Management for System Administrators, updated with today's tools and techniques?
Oh, great question. So I don't currently have plans to update that book, but and though it needs it, it still talks about PDAs instead of cell phones or smartphones. I do want to say that the techniques listed in that are if I did rewrite it, it would not have to be a very big rewrite because the techniques are basically what people have rediscovered now as DevOps and stuff. But it is something I think about maybe in a couple of years.
Okay, thank you. Another question is how can we apply these techniques to make large software programs more resilient? I guess if you want to elaborate a little bit more on that.
Sure. A lot of these resiliency techniques are going to work best when you've designed the system from the beginning to use to be able to run on multiple machines, like running behind a load balancer. But also, one of my favorite techniques that I didn't mention in the talk is called feature flags, which is where every time you add a new feature to software, add a flag that enables that feature. So you can run the software in production with the flag off until you've really finished writing the feature. Meanwhile, you can test the feature in your beta environment with the flag on. Now, when it's time to run when you want to enable that feature, you can flip the flag, and it's the software that you've already deployed, but you've just changed a flag to enable that feature. If you do find a bug, you can flip that flag back off again, or if maybe it's not a bug, but maybe it's just not performing well. There's another technique that I like, which is if you're not sure if your software is going to scale very well, if say a new feature might not scale very well, you can, and we talk about this in the book, Facebook, when they launched chat, they knew that the moment they announced chat, 1 million or 1 billion people, whatever, we're going to try that feature all within minutes, and they weren't sure if it was going to scale to be able to handle that. So what they did was the JavaScript that you download when you're viewing Facebook sent test messages across their chat system. So everyone using Facebook was beta testing the chat system. They didn't even know it. And they were able to determine that, yes, it does scale. Or actually, they determined it didn't scale, and they had months to fix it. And then when they actually launched the feature visibly, it was already running in your browser. They just made that chat window visible. And it's been suggested that every big feature that Facebook is going to launch in the next 6 months is probably running in your browser today. It's just invisible and running in some kind of test mode to make sure everything scales.
Great, thank you. Could you talk a little bit about what you use for documentation?
I'm a big fan of wikis. Currently, I'm using the wiki that's built into GitLab, which is a very minimalistic wiki, but it's it's good enough. The reason I like wikis in general is that it lets me just constantly be updating the wiki, and because things are always changing, and you always want to you want to be effortless in your ability to update the docs. I literally have 2 monitors on my desk because one monitor is where I do my work, and the other monitor I keep my wiki open. I'm either following a procedure that myself or someone on my team wrote, or I'm updating the page as I'm doing the procedure.
Very good advice. Yeah, do you have any experience in large enterprise systems or legacy ERP systems with a lot of history? And do you think these ideas can be implemented there?
I think they absolutely can. And in fact, applying like DevOps principles to large legacy systems is a really hot topic, and I'm really excited about it. The key is you need to be able to, in an automated fashion, run a battery of tests on the system so that if you're making a change, you can run that battery of tests and have the confidence to deploy this new software release. And that whole automated testing and deployment infrastructure is often called a CI/CD, continuous integration, continuous deployment. And people often think about CI/CD as, well, it's automation that just makes it faster to deploy software. Speed is nice, but the awesome thing of CI/CD is the confidence you get. And if you can implement CI/CD and get that confidence to deploy new releases, it doesn't matter if you're on the latest Linux system or a 30-year-old mainframe. And in fact, I have friends at IBM that say you can do all of this with their biggest mainframes and that they do it. And it's just a matter of taking the time to develop those things, which is, of course, a big challenge. And my recommendation in that area is start small. You know, automate one little thing and make that a success, and success builds more success. People will want to copy that success. So you can automate just one aspect of the testing of a system, and then another aspect, and build and build and build until you have that perfect CI/CD workflow.
Good. Thank you. How about the failure tests? Do they run in live systems, or do they run on non-live test networks?
Most companies, well, I recommend you start on in a test environment, and once you've perfected all of your techniques, then do them in the live environment. Obviously, you're going to need more manager permission to do it in the live environment.
Right.
But we think that our test environment is the same as our production environment, but they're never exactly the same. So I highly recommend that you perfect it to the point where you have the confidence to do it in the live environment. And when management pushes back, phrase it this way. Say, there is going to be a problem someday. Do you want us to learn how to fix that problem on a Saturday night when it's hard to find the key developers and et cetera, or do we want to find that problem, on a Wednesday at 1 o'clock when everyone's here in the office and awake and ready? And that's really the way you sell that to management.
Right. Okay. Well, we have many more questions, but Tom kindly offered to answer them in writing. So I'm afraid we ran out of time right now. So I would like to thank Tom Limoncelli again for his informative presentation and insightful answers to the many questions. A special thanks to each of you for taking the time to attend and participate today. Now, this webinar was recorded and will be available online in a few days at learning.acm.org/webinar. You can find announcements on upcoming webinars and other ACM activities at learning.acm.org and acm.org. Also, please fill out our quick survey where you can suggest future topics or speakers, which you should see in your screen. So on behalf of ACM, Tom Limoncelli and myself, Indira Guzman, thank you again for joining us, and I hope you will join us again in the future. This concludes the webinar.